Hey everyone, to a new awesome video, and today we are going to continue with our series about electricity and magnetism. Today we will start exploring the world of conductors and insulators. First of all, we will understand what three rules make a conductor, and does it have to follow, and the difference between conductors and insulators. After that, we will analyze how a conductor behaves under the influence of external charges, and we will also analyze how a conductor behaves under the influence of internal charges that are surrounded completely by the conductor. So let's start. Alright, there are three rules or three consequences that happen in a conductor. So that you understand it, basically, a conductor is a material in which electrons can move freely. That brings some serious consequences. First of all, is that if electrons can move freely, they are going to follow the lines, the electric field lines that may form until there is no electric field. So, first consequence is that the electric field equals 0 on the inside of those conductors. Every charge is going to be positioned at the ends of the conductor, at the surfaces, and it's going to cancel in such a way that the inside charge, inside electric field is always going to be 0. Another consequence that is a direct consequence of that fact is that if you have, for example, a point over here and another point, and you move through them, as the electric field is 0, you know that difference in electric potential, is going to be 0. And you reach the second conclusion. That is that all points inside the conductor are at the same potential. The last fact that you may find is that, for example, imagine drawing a Gaussian surface inside of this conductor right around here. There is no electric field that goes in or goes out because, as we said from our first consequence, the electric field is 0. Therefore, by Gauss' law, we conclude that if the electric field is 0, the electric flux is going to be equal to 0, and by Gauss' law this is equal to the charge enclosed over epsilon naught, which means that the charge enclosed equals 0, and therefore the charge density inside of the conductor for all of it equals 0. These are the three most important things to know about a conductor, and let me label this as the third one. That helps you differentiate them between conductors and insulators. It is also important to mention that there are some materials that are semiconductors. They let some electrons move, but maybe not all of them. And in some cases, they will have similar properties to these ones, but not in that extreme. Maybe there's a little bit of change in the electric potential, there is actually a little bit of charge density inside of the conductor, and the electric field is not exactly equal to 0, but usually we can maybe approximate to one side or the other. Right, now let's analyze what happens to a conductor when there is external charge over there. As electrons are free to move and there is a positive charge right here, they are going to move towards the positive charge, and they are going to move to the outer surface because we said that the charge inside the conductor is going to be 0. Therefore, there's going to be an induced, because it has been created by the electric charge, an induced positive, well, in this case, sorry, negative superficial charge density along this surface. And in return, there's going to be some protons that are going to be left without electrons because the electrons have moved over here. Therefore, we're going to have some positive over here, some positive induced charge density on the surface. And what happens is that the electric field inside of the conductor, the E inside, is going to be equal to the external field by the principle of superposition plus the field that is induced. And this induced field works in such a way that they cancel each other so that the field inside is zero, and this effectively behaves as a conductor with a zero internal electric field. Great, now let's analyze the situation in which we have a conductor that it might be charged. Let's say it had an initial charge of Q0 on the external and internal parts in total, a total charge of Q0. And now we're going to have an internal charge over here. So what this charge is going to generate is something pretty similar to what happened before. We're going to have some electrons that are going to move over here, and they are going to create an induced, once again, induced negative. It's going to generate an induced charge density on the inside. We'll call it inside, induced on the inside. And this charge density, we can calculate that it is going to be zero. It's going to be equal to this charge, because if we draw a Gaussian surface over here, by our first rule, the electric field to this surface will be zero. However, the charge inside, for that to be the case, has to also be zero. Therefore, we know that the total charge inside, Q induced inside, which is equal to the integral, the surface integral of this induced charge density over the surface, this charge plus Q, so this plus Q has to be equal to zero. Therefore, we conclude that this induced charge density in the inside equals minus Q, and therefore this integral equals minus Q. However, as before, we're also going to have some protons that are left alone on the outside of this region. Therefore, what we are going to have is some superficial induced outside charge density. And this superficial outside positive induced charge density, so induced outside, is going to create a charge in a similar manner. So Q outside induced, well, I swapped the indices, but it doesn't matter. That is going to have a very similar form, but to another surface, the outside surface. And we can use, once again, Gauss' law to find what this is going to be. We know that this superficial outside charge is going to be equal to the charge outside. We know that the total charge that is going to be inside this system, if we drew a Gaussian surface surrounding it all, is going to be equal to Q0 plus Q. And now we know this is going to be equal to the Q out plus the Q the Q inside, plus Q. Therefore, we find that these two terms cancel each other, the Q's with the Q, and we find that the charge outside plus the charge inside equals the Q0. And we can solve for the charge outside, Q out, which is going to be Q0 minus this Q inside. However, we already have an expression for this, which is minus Q, and if we plug it in, we find this is plus Q. So this is going to be the charge density, well, the charge that is going to pile up all throughout the outer surface. And note a very important thing, that if this is spherical on the outside, it is not going to matter where we put this charge on the inside, but what everything on the outside is going to feel is this charge coming from the center of mass of this object. So it doesn't matter where you move this charge, that the outside will feel the same regardless of the position, and that is a very useful thing when dealing with conductors. That is all for today. I hope that you got a sense of the differences between conductors and insulators, and also how these properties about conductors can be used to our advantage in different situations, such as shielding, as we saw, when there is a charge but on the inside of the conductor you don't feel anything. That's similar to what happens in cars when a lightning strikes them. The conductor on the outside shields the people on its inside from any charge that strikes the car, and also this effect of redistributing any charge that is on the inside to the outside in a perfectly compensated manner. Any doubts left, you may ask them in the comment section and I try to answer them in the best way I can. Remember to like the video if this was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!